Hey everybody, I'm going to get started. I have on the screen there, oops, here we go. I have on the screen some transformation questions. So here I've got point P located at 10, 1. And there's all kinds of transformations. But 1, 2, 3, 4, 5, 6. Here's 7 of the most common transformations. That is rotating by 90 degrees, counterclockwise, rotating 180, 270, some kind of dilation, and reflecting over the x-axis, the y-axis, and the y equals x line. So take a minute and if you sketch that point 10-1 on your notes that you're taking, I think you'll be able to, even without having formulas for rotation of 90 degrees, 180 and all that, just by approximating where that point would end up after the transformation, I think you can figure out the coordinates. So everyone take a few minutes on that. Okay, so you had some time to think about the different answers. Of course, all the answers, what are all the answers going to have in common? Someone type into the chat, what are all answers, all 7 answers going to have, well, at least 6 of the 7 answers are going to have in common? And I mean specifically when the point P is 10-1, what is going to be true for all the answers except for maybe one of them? Well, why don't we go this way? Will someone say what the answer to the first question is when you rotate by 90 degrees counterclockwise? Mm-hmm. Yes, negative 110 is the right answer. When you rotate, it ends up somewhere over here in quadrant 2. You see, if it was on the x-axis and you rotated 90 degrees, it would end up on the y-axis. But because this is slightly above the x-axis, when I rotate 90 degrees, it's going to be over here to the left. And the thing that all these answers have in common is that they have a 10 and a 1 involved somehow. So this one's got to be negative 1, 10. The only answer that does not have a 10 and a 1 in it is question number 4. When you dilate, the x and y values get doubles and it ends up at 22. But all other answers have a 10 and a 1. Sometimes the 10 is the x coordinate, sometimes the 10 is the y coordinate, sometimes the x coordinate's negative, sometimes the x coordinate's positive, but a lot of 10s and 1s. Well, what we're going to see today is that one of the most important uses of matrices is that they can be used as a way to describe transformations, geometrical transformations. And when you're able to do that, this matrix, which is kind of like a number, but it's a rectangle of numbers, when when you can use that to describe geometrical things, it gives us a language for describing transformations in a way when we can add and subtract and multiply matrices. It gives us a way of getting even more details about transformations. Here are, you don't need to write these down, but here are the 7 transformations written in more like general terms, not with 10-1, but real generally, like if I take xy and rotate it 90 degrees, it ends up becoming negative y comma x. And we can see here the 7 transformations, plus I made up an 8th transformation, which I put here. I'll be using it as an instructive example. xy turns into 5x plus 2y and 3x minus y. So that's a complicated transformation. It's not quite a rotation. It's not quite a reflection or a dilation, some kind of weird other thing. But it is very easy to use the definition. So that means the 10-1, I would do 5 times 10 plus 2 times 1 to get 52, and 3 times 10 minus 1 to get 29. So what, each of these transformations makes a single point go to some other point. Transformations get more interesting when you start taking an entire shape and you transform, every point in that shape, and now you get some kind of distorted shape or something like that, or rotated shape. And so if you would make a note of this transformation. Now, I want to show you how we can model transformations with matrices. Let's say I take the point 10-1. We're going to write the point as a 2-by-1 matrix. That's the point 10-1. And on the left is going to be a 2-by-2 matrix. And we want to get minus 110 as the answer. So it's kind of weird. It's like an algebra problem. What matrix has to go here so that when you multiply it by 10-1, the answer is negative 110. And it is pretty tricky. Does anyone know what the answer is? You could just put the 4 numbers from top left to top right to bottom left to bottom right. Okay, does anyone come up with what the 4 numbers? 0. Oh, well, it's going to be a 2-by-2 matrix. Yes, 0, minus 1. Let's see if that's right. 0, minus 1, 1, 0. If I take the first row with the 1 and only column, I get 0 times 10 is 0, plus negative 1 times 1 is negative 1. And if I take the second row with the 1 and only column, I get 1 times 10 is 10. So that did work. The second one might be easier to understand. I want to go sort of more generally now. So I have the point is x, y. The result is going to be 5x plus 2y and 3x minus y. That is a 2-by-1 matrix, even though it doesn't really, it looks like it's, this plus doesn't get me into a new element. It's still part of the same one. This one might actually be a little easier to see. So how would you get 5x plus 2y, 3x minus y? You could type it in to the comments. Except it's going to be a 2-by-2 matrix. Yes, there it is, the full part. So it does become 5, 2, 3, negative 1. These four coefficients. And you can see when you test it, oh, is it right? Well, 5, 2 multiplied by xy becomes 5x plus 2y, just like we hoped it would. And 3, negative 1 multiplied by this xy becomes 3x minus y, just like we hoped it would. So in general, like we could even take this original one and we could write it as 0x minus 1y, comma, 1x plus 0y. And if we did that, we could actually see the four numbers 0, 0, minus 1 ends up there, and 1, 0 ends up there. So you could just take any transformation that's like this. If you can write the transformation in the form ax plus by, comma, cx plus dy, if you can write it in that form, then it can be modeled with the matrix A, B, C, D, and you can put the xy point on the right, and it will turn into that transformation. So we'll keep that in mind. Okay, here's some practice questions for you. And there's not so many people, but I am going to put you, actually, why don't we all just be in one big room? So I'm going to push pause on the recording. Okay, everybody, I was not able to see all the, see if you were talking or not. For some reason, I'm not seeing all that, all the little screens. Nonetheless, here are the answers. And hopefully you got all these answers. So all the transformations can be modeled. And I guess the trick, if you ever got confused, you can take the transformation like this one, xy becomes y comma x. But if you write that yx as 0x plus y plus 1y, comma 1x plus 0y, then these four numbers, 0, 1, 1, 0, become the four numbers in the answer. Here we go. Thanks. For some reason, the screen got blacked out, but it's okay now. Okay, so what can we do with this? Well, here comes one of the most challenging questions and interesting questions, in my opinion, that we see this whole semester. And this is really, so far what we've seen today is that transformations, at least two-dimensional in a XY plane, you could describe transformations as multiplications by certain 2x2 matrices. And those cause some like a dilation or a reflection, usually, or a combination. But what about a rotation? So here comes a question with a numerical, oh, someone wanted this back. Okay, so here are the answers to those. And I'll be posting this video up as well. And actually the notes from a previous year already posted for you. Okay, now I have the challenging question now. And I'd like to give you at least 5. Oh, well, here's what the question is. What if you take the point 10, 1 and rotate it not 90 degrees, but only 60 degrees? What are the coordinates of the point in that case? And that is a very challenging question. Why don't you guys mess around with that question for at least 5 minutes? Now, there is a way to do it with no calculator and no trigonometry. However, I will allow you to use anything you want, including trigonometry, to help you answer this question. So everyone take a few minutes. I'm going to pause the video and give you at least 5 minutes. Okay, everybody. Now, one way to do this is to make a picture kind of like this. Look what I've done. I have created a right triangle. See that upright right triangle? This one over here? Well, these two sides of that right triangle, the horizontal and the vertical side of the right triangle, will be the coordinates of that point. Well, the hypotenuse of that right triangle is square root of 101, because it's the same length if I go from the origin to P and I rotate it around the origin 60 degrees, that's also going to be the square root of 101. But that angle, this is a right triangle, but the 60-degree angle is not, this is not a 30, 60, 90 triangle. It's a 36, it's not a 60-degree angle there. It's a 65.7 degree angle, because if you do tan inverse of 10 over 1, you get 5.7. See, this angle, this from here to here is 60 degrees, but you got this little extra part that's 5.7 degrees. So if you do that, you can then calculate these side lengths by doing SOHCAHTOA, basically. Square root of 101 times cosine 65.7 is about 4.13. And square root of 101 times sine 65.7 is about 9.16. Well, that method would require trigonometry, because you need a calculator, because otherwise, one, you wouldn't know that it was a 5.7 degree angle, that this small angle, formed by the x-axis and the initial 0 to 10, 1 line segment. And then you would need a calculator again, because you have to do cosine and sine of 65.7. So it would require 3 uses of the calculator. But this question could actually be done with no calculator. And it's going to have a very clever formula associated with it. Okay, so take a look. What I've done here is I've taken, and this is the big, difficult part of today's lesson. What I've done is I've taken the 10-1 point, and I've written it as square root of 101 cosine 5.7, square root of 101 sine 5.7. Now, I know I was telling you could do this without a calculator. Well, you will be able to, but just for instructional purposes, it's true that it could always be written as something like this, whether we know what those two numbers are or not. May or may not be, important for us, but at least in this case, let's just say I know the 5.7. And after the rotation by whatever number of degrees, 60 degrees, or just call it theta degrees, the points written in this trigonometric form would be square root of 101 cosine theta plus 5.7 degrees, comma, square root of 101 sine theta plus 5.7 degrees. Okay, so here comes the big lesson. So the 10-1 can be written as radical 101 cosine 5.7 and radical 101 sine 5.7. There's going to be a mysterious matrix here that after I multiply the matrices together, it will now be root 101 cosine 5.7 plus theta and root 101 sine 5.7 plus theta. Now that seems like a lot to ask of these four numbers. It's not like before where we had like a goal of 5x plus 2y and 3x minus y. Our goal is this. Anyone have a thought of how we could make some progress on that? Because this is my goal, but maybe there's something equivalent to that goal that might be more achievable. I want to type in what might be more achievable than radical 101 cosine 5.7 plus theta. It might be more complicated, but it also might be more feasible. Anyone have a thought on that? Remember that in all the ones that we've done before, the transformations had the form kind of like this, something plus something, something plus something, or maybe minus. Okay, anyone have a suggestion? Yes, the addition identities, because this thing is the same thing as saying root 101, the cosine A plus B formula is cosine 5.7 cosine theta minus sine 5.7 sine theta. And if you don't mind, I'm going to throw the square root of 101, distribute it to both of those. And this would be square root of 101. The sine A plus B formula is sine A cosine B plus cosine A sine B. So it's sine 5.7 cosine theta plus cosine 5.7 sine theta. Well, now square root of 101 cosine 5.7 square root of 101 sine 5.7. Does someone have a suggestion about what these four things are so that these four things ends up happening? Maybe we should start with just how can we get this to happen? Oh, sorry, how can we get this to happen? Those are the things that get combined. So how's that going to happen? Yes, cosine theta and negative sine theta will accomplish that. So this is cosine theta, because then you would get cosine theta times this thing would become that. But to get this minus sine 5.7 sine theta, this thing has to be minus sine theta. Now, what about these two guys in order to get this second row to happen? I realize this will be better if I write it as cosine 5.7 sine theta. It's equivalent, but it will be better for our purposes, I think. Yes, and Jessica says, oh no, that was the one from before. Okay, how about this one? My goal is to get square root of 101 cosine 5.7 times sine theta, and yes, sine theta cosine theta. And that gives us the big formula. This is the formula. This is the 2x2 matrix that causes a 60-degree rotation. I'm sorry, that causes a theta degree rotation. And what's nice about this is, remember before you said, well, I don't have a calculator, so I didn't know that 10(1) was radical 101 cosine 5.7, radical 101 sine 5.7. That's okay, because the 10(1)'s there. And then I just put here cosine 60 minus sine 60, sine 60, cosine 60, which is 1/2 negative radical 3/2, radical 3/2, 1/2. Times 10(1). I end up with 1/2 times 10 is 5. Radical 3/2 times 1 is negative radical 3/2. And for the other row, I get 5 radical 3 plus 1/2. So those are the exact answers for the location of 10(1) when it's rotated by 60 degrees. Now you would need a calculator if this angle was not some kind of, had a either 30, 45, 60, or some sort of thing that has it as the reference angle. But that's a really clever formula. And it has a really clever way of getting to it with the sine A plus B and cosine A plus B formulas that you did last semester. This formula, so here's the general formula. That's like the big thing for today. And just so you know, when theta equals 90, just to kind of go full circle, cosine of 90 is 0, minus sine 90 is -1, sine of 90 is 1, cosine 90 is 0, and we end up with the same answer we got earlier when we figured out, I think it was the very first question on this sheet, on this one, the 0, -1, 1, 0. So it comes out to be exactly the same thing. Okay, I have over here one quick thing to show you. In the class page, that one of the resources is Geogebra Collection, and here you have this point E that you can drag around, and here I have this M, this matrix, and 1, 0, 0, 1 doesn't do any transformation, but it's fun to kind of mess around by changing these sliders. And you can see, if I change it to 2 and 2, A and D, both to 2s, or in this case, 2 and 3, you can see it turns into a dilation. That's strange. It's not proportional. The axes aren't proportional. I need to fix that. Anyway, by messing around, by making the matrix more involved, it's not that clear, what's going on with it, but we can at least sort of see some stuff happening when I move the point. Okay, so that is what I wanted to show you for today. The goal of today was to have an understanding that 2x2 matrices, if you put them on the left of a 2x1 matrix, it models geometric transformations. And it led all the way up to a very surprising formula: cosine theta, negative sine theta, cosine theta, the rotation matrix by angle theta. As long as you know sine and cosine of the angle, you could do it then. Okay, so that's going to do it for today's lesson. Let me stop the recording.